So today we're going to use calculus and the methods of slicing that we've been developing for a couple of classes to calculate the mass of objects that are not uniformly dense. So quick example that involves no calculus. I want to find the weight of a cube that has a side length 3 inches, so 3 by 3 by 3, that is a density of 2 pounds per cubic inch. How do we calculate that? Yep. So 3 cubed, and that is 27 cubic inches, right? Because it's inches by inches by inches. So cubic inches, and then times 2 pounds per cubic inch, and then your cubic inches cancel, and you end up with just pounds. 27 times 2 is 54 pounds. So in general, density is the concentration of stuff in an object. It's usually measured in units of mass per volume. For example, grams per cubic centimeter, or sometimes units of weight per volume, like pounds per cubic feet. So a solid object that has uniform density satisfies this basic relationship. Mass or weight, right? That I shouldn't have used the slash because it looks like a fraction. It's supposed to be or. Mass or weight is just volume times density. And you can also use density for 1- or 2-dimensional objects. So mass or weight is length times density. And mass or weight could be area times density in the 2-dimensional case. However, when the density of an object is not constant, it might vary, those formulas no longer hold. So what we're going to do is we're going to use calculus to calculate the total mass of the object. So to do this, you slice the object up in such a way that each slice has approximately uniform density. So when you're deciding how to slice, you want to choose a slice where the density in that slice is approximately the same everywhere. Then you use the easy formula on each slice, and then you add up all the slices. And once you let the number of slices go to infinity, that's an integral. So let's do an example. We have an open cylindrical barrel, diameter 7 feet, and height 21 feet, filled to a depth of 10 feet with muddy water. Okay, so I'm going to draw a picture. A cylindrical barrel. The diameter is 7 feet. The height is 21 feet. And it's filled to a depth of 10 feet with muddy water. So we've got water at a height of 10 feet. Okay, the density of the water varies linearly with the depth of the water. So the density of the mud in the water, right? Because the mud tends to settle towards the bottom. So it's denser at the bottom than it is at the top. And they said that the density at the bottom is 80 pounds per cubic foot, and the density at the top is 30 pounds per cubic foot. And we want to find the total weight of the muddy water in the cylindrical barrel. Okay, so before I even do any slicing, I want to write an equation that will tell me the density at a height of h. So if I want to look at a particular height, let's see, I'm going to try to draw a slice of water. So I've got like a disk of water at a height of h. So at that particular height, I'm taking a thin like slice of the water. The density at that small thin slice is going to be approximately uniform, the density of the water. So I need to know the density at the height. So I can calculate the density at any given h by using this given information. So they basically gave me 2 points, right? So I've got h values and density values. Common letter that we use for density is delta. So they told me that at the bottom of the barrel, so what is H when we're at the bottom of the barrel based on the diagram I drew? 0. So at the bottom of the barrel, the density is 80 pounds per cubic foot. And at the top, when I hit the top of the water, at how high is the water level? 10 feet. So at the top, 10 feet, the density is 30 pounds per cubic foot. So I have 2 points. It varies linearly, they told me, which means I can just write a line that connects these 2 points. I'm going to write equation of a line that connects these. So I need the slope of the line. So that's going to be 80 minus 30 over 10 minus 0, which is -5. So my equation for H, because I did the subtraction backwards, 80 minus 30, then I have to do 0 minus 10, right? Because the 0 goes with the 80. So that comes out to -5. So my density as a function of height is going to be -5h plus y-intercept, which would be what? 80. Yeah, because I know that when h is 0, delta is 80. So -5h plus 80. So I've written the equation of a line that tells me the density at any particular height h. Okay, so now I have this slice of water, muddy water, at a height of h. I want to calculate its weight. I want the weight of that just slab of water. So the weight of the slab is equal to the volume of the slab times the density of the slab. Volume times density tells me weight, because volume is going to tell me cubic feet, and the density tells me pounds per cubic feet. All right, so the volume of this disk of water is pi r squared h, and then the density of the slab is delta of h, okay? The density at a given height. Okay, what is the radius of this slab of water? 3.5. Yep, it's just half the diameter because the radius is the same all the way up and down the cylinder. So that's a constant. So this is pi times 3.5 squared times, what is the height of this really skinny cylinder? What should I call it? That's the height from the bottom up to my slice. I just want the height of my slice. Delta H, right? Yeah, it's some small change in the height. And then the density at height h is given by the formula -5h plus 80. Does that make sense? Okay. Now I'm going to stack up these slices. I'm going to have like all these slices of water, slabs of water, each one having approximately uniform density. There's another one. I'm adding up n of them. I'm going to start at the bottom when h is 0, and I'm going to stack these slabs of water up until I hit the top of the water level, which is 10 feet. And so I need to add these all up. So the volume of the weight of all the slabs is the sum from I equals 1 to n. Every slab has this weight. I'm going to throw some i's on here now because I'm doing this at like lots of different h values. 5h sub I plus 80 delta h. And then to get the exact weight, now I just take the limit as n goes to infinity. So the weight exact is the limit as the number of slabs I'm stacking up goes to infinity, and the delta H, the thickness of each slab, goes to 0. The sum from I equals 1 to n pi is 3.5 squared times -5 hi plus 80 delta H. And that is the definition of an integral. That's a limit of a Riemann sum, so that's an integral. Drop the sub i's. When delta H goes to 0, that becomes a dH. And my bounds of integration are where I'm stacking the slabs of water. So I'm starting at H equals 0, and I'm stacking them up until I hit H equals 10 feet. So 0 to 10. So with these applications of the integral, when this is like a real life thing, it's a barrel of muddy water, and I'm asking you how much it weighs, it makes sense to get an approximate number that doesn't have pi's in it, like just a number, rounded number, so that we can ask ourselves if this answer makes sense, right? Like, does it make sense for this large barrel of water to weigh this much? So I'm just going to have my calculator evaluate this integral. Okay, so the syntax for evaluating an integral on your calculator, you're going to be doing this in the activities, so I'm just reminding you how it works. So we're going to go math. You choose fint for f function integration. It's option 9. And if you have a newer calculator, you just type in all the, you make the calculator look like your integral. And if you have an older calculator, I'll remind you of the syntax when you're working on the activities. So I'm integrating from 0 to 10 pi times 3.5 squared times -5. I'm using x because that's the variable on my calculator. -5x plus 80 dx. All right, that should do it. And I get about 21,166.48. And the units on this would be pounds, because this is the exact weight. So does that make sense for 10 feet of water, radius 3.5, muddy water, to weigh that much? Yeah, water is really heavy, and that's a lot of water. And it has mud in it, yeah. Okay, so that's the idea. You want to slice things up so that each slice has approximately uniform density. Add up the weight of all the slices.